When formalizing the topics of probability, we really rely on the mathematical tool of sets. Now, sets are things that we discuss colloquially as well, and so we're often going to be talking about a set of some type of items, for instance. However, in mathematics, we're thinking about sets as a very specific mathematical object with specific ways of manipulating the sets. And so in order to really understand the fundamentals of probability, we need to first make sure that we understand the fundamentals of sets. So to formally express probability in a mathematical language, we use the concept of sets. And in math, just like in the real world, sets are collections of objects. However, when we're talking about them mathematically, we're going to have mathematical rules that govern their behavior. So to think about sets as they relate to statistical experiments, our sample space, which is the set of all possible outcomes from an experiment, is going to be defined as a mathematical set. For instance, if you think about rolling a die, you might have the set 1, 2, 3, 4, 5, 6. It's going to be the set of all possible outcomes that can occur if you roll a die. And we're thinking about this as being a mathematical object that contains representations of all of those different outcomes. Now, events themselves are defined to be subsets of the sample space. And subsets are really just going to be sets themselves. So a subset is defined where every element in that set is contained in the larger set itself. So each element inside of an event has to be inside of the sample space. Right? If we take, for instance, the event 2, 3, this is going to be a subset of our sample space 1, 2, 3, 4, 5, because the 2 is in the larger set and the 3 is in the larger set. If instead we had said something like E1 was going to be the set containing 2 and 7, this is not going to be a valid event. It's not going to be a valid subset because that 7 is not in our sample space. In order for something to be a valid subset, everything inside of it has to live inside of the larger set. And so in the case of events and sample spaces, everything inside of an event has to exist inside of the sample space. Now, if we wanted to talk about how big an event is, how many different outcomes are contained in the event, then we can use this notation here that looks a little bit like taking the absolute value, or looks exactly like taking the absolute value, actually. And so when we're talking about this, what we're really referring to is the size of the set. So we're talking about how many elements are actually contained within it. And so we might call this the magnitude of the set, but we can also just think about it as being the size of the set more broadly. And so if we have a set that has, or an event that has a size that is greater than 1, we call this a compound event. If we have a set that has a size of 1, and it's an event, then we call this a simple event. And so all of the language that we're thinking about, sample spaces, events, simple versus compound events, can all be framed through mathematical sets here. Now, when we're dealing with sets, we want to know how can we actually manipulate sets? If we have one set, how can we do things to it? How can we take multiple sets and join them together or separate them, right? How can we actually sort of use operations around it? And the analogy that we're thinking about is that if we're given a bunch of numbers, then we know that there are these elementary algebraic operations that we can use to manipulate numbers. So you can add them, you can subtract them, multiply and divide them. And all of these are going to give us sort of the foundations from which we can build more complex expressions, we can write down more complicated formulas, and so forth. And so when we're dealing with sets, what we want is something that's going to be analogous to these different operations here, except instead of adding or subtracting or multiplying, we're going to want to do things that are actually relevant to the sets themselves. And so we can define what we'll call elementary set operations in order to manipulate sets in the same way that the elementary algebraic operations manipulate numbers. The first that we're going to think about is called the union. And the union is going to take in 2 or more sets. And what it's going to do is it's going to take all of the elements from all of the sets and form one new, larger combined set. So you take everything from your first event, you take everything from your second event, and you combine them together. In some sense, this is a little bit like addition, right? But if you have a set over here and a set over here, and you want to join them together, we can say that we're going to take the union of it. If we want to write down what the union is, we're going to use this U symbol here. Okay? So the union is written with this U, and A union B means we take everything that's inside of A, we take everything that's inside of B, and then we write out the new set containing all of those elements. The intersection is our second elementary set operation, and instead of us taking everything from both sets, what we're going to do is we're just going to think about what is common to both of the sets. So we're looking at where do these two sets overlap? What are the elements that are in set A and the elements that are in set B? So the union takes everything from both. The intersection is just going to take what's common to the two of them. If we want to take the intersection between two sets A and B, then we use this upside down version of the union symbol. So it looks a little bit like an N without the tail, right? And so this would be A intersect B. And what we're saying here is that we're looking at what's in A, and then from everything that's in A, what is also in B? And we're going to form a set that contains just those elements. The third and final elementary set operation that we're going to talk about is the complement. Now, the complement acts on a single set. We don't actually need two sets here. And what it's going to do is it's going to say, we're going to take everything that is not in the set that we're given. And so if we have our sample space and we have an event and we want to say, okay, everything that's in this event, how do we refer to all of the other stuff that may have happened? Well, we use the complement here. And so for some set A, we refer to the complement as A with this exponent of a C, the C being for complement here. And so between the union, the intersection, and the complement, we're really going to be able to manipulate sets in really effective ways and start to talk about more complicated events and start to really break these down using these elementary set operations. So let's look at some examples here. Suppose that we have our sample space as just the numbers 1, 2, 3, and 4. The first set, E1, is an event here. It's 1, 2, and 3. So this would be a compound event because there's more than one element in it. E2 is just the event of a 1 occurring. And so this is a simple event. And E3 is also a simple event. It's just the event that the 2 occurs. And so the first question, well, what's the union of E2 and E3? And remember, the union is going to take everything that's in E2 and everything that's in E3, combine them together. And so with E2, we come up and we see, well, the E2 is simply a 1, right? And so because we just have the 1 here, then we're going to have the 1 in our set. And then we go to E3 and we say, well, what's in E3? It's just this 2. Okay? And so then we're going to take the set that has a 1 and a 2 in it. And so the union of E2 and E3 is 1 and 2. What is the union of E1 and E3? And so again, we'll go here and we look at the set E1, right? And so we know that we're going to include a 1, a 2, and a 3. Okay? And then we go over to E3 and we say, okay, well, that's going to be a 2. And so we want to include the 2 in the set as well. But notice the 2 is already in the set, right? The 2 was here from E1. And so one really common important rule to note is that when we're writing down sets, we don't duplicate items in them. Okay? And so instead of this being 1, 2, 3, and then another 2, we're just going to leave it as 1, 2, 3. So E1 union E3, or union E3 is going to be 1, 2, 3. Right? We never duplicate those items. Part C, what's the intersection of E1 and E2? So remember, the intersection asked us, well, what is common between these two different sets here? And so the first thing we're going to do is we're going to go to E1 and we're going to say, okay, we're starting with a 1, a 2, and a 3. And then we go and we ask, well, which of these is also in E2? And we say, is the 1 in E2? And it is, right? So we keep the 1 there. Is the 2 in E2? It's not, so we're going to be removing that. Is the 3 in E2? It's not, so we'll remove that. And we're left with just the set that contains a 1 here. Right? So the intersection of E1 and E2 is just a 1. Okay. What's the complement of E1? Now with the complement, remember what we're doing is we're going over to our full sample space, right? And we're saying, okay, what is in our sample space, but that's not in our set E1? And so we can start with our sample space here, and then we can ask ourselves, is the 1 in E1? And it is. Is the 2 in E1? It is. Is the 3 in E1? It is. And so then the only element that's not in our set E1 is going to be the 4 here, right? And so if we take the set that just contains a 4 in it, right, that is going to be the complement of E1 because that contains everything that's in our sample space, but that's not in our overarching set here. Okay. Continuing on, what is the intersection of E1 and E2 complement? Okay. And so here we want to start to think through these in sort of a compound kind of way. And so we'll actually write down what our sort of thought process is here, right? We want to take E1 intersect E2 complement, okay? And so we can sort of work through this still on left to right, right? We know that what we're going to want to look at is what are the elements that are shared between E1 and E2 complement. And so what we really need to do is we need to write down, well, what is this set E2 complement here? Okay, and so E2 complement, remember, what we're going to do is we're going to take our sample space and we're going to remove everything that's in E2. In other words, we want to say what is not in E2. And so if we go through here, well, the 1 is in E2, but the 2, the 3, and the 4 are not in E2, right? And so as a result, E2 complement is going to be the set 2, 3, and 4. And so then if we take E1 intersect 2, 3, 4, we're asking, well, what is shared between these two sets? And we notice that the 2 and the 3 are in both of them, right? And so ultimately, this is going to be the set 2, 3, right? And so we can walk through that one more time, right? Where just remove these notes here, okay? E2 complement is going to be the set 2, 3, and 4, okay? E1 intersect E2 complement is thus going to be 2 and 3 because that's what's shared between our 2, our 3, and our 4 and the set 1, 2, 3. Okay. Now we have a slightly longer expression here. What is E1 complement union E2, all complemented intersecting with E3 complement? So I would encourage you to take a moment and try to work through this. And again, just work through it piece by piece here and going left to right, working inside brackets first where you need to. But if you want to see how this is done, right, again, we'll take this one single piece at a time. So we start here with wanting to think about E1 complement, right? An E1 complement is everything that's not in E1. So that's just the set 4 here. Okay. And so what happens if we take E1 complement union E2? So if we want E1 complement union E2, that's going to be, well, what's in E1 complement and then also what's in E2? And we're going to be seeing that that's going to be a 4 and then E2 is just the set 1. So then we have 1 and 4. Okay. And so then if we want to take the complement of this set, right, E1 complement union E2, all complemented, we have to say, well, what is not in this set? Right, that set is a 1 and a 4, and so the complement of that is going to be a 2 and a 3. And then if we want to intersect that with E3 complement, well, we need to first know, well, what is E3 complement? Right, E3 complement is going to be what's not in E3. E3 is just 2, and so that's going to be a 1, a 3, and a 4. Okay, and so then if we want to intersect this set here with this set here, we're saying what's the same between both of them, and the only thing that's common between both of them is this 3. Right? And so again, piece by piece, we can work through all of those using our elementary set operations here. Okay, and so how do we do this? Well, E3 complement is 1, 3, and 4. E1 complement is just the set 4. So if we take the union of E1 complement with E2, we get the set 1 and 4. And so the complement of that is going to be 2, 3. So then we intersect those two sets together and we just get the set 3. The final example here, what is the intersection between E2 and E3? So E2 is just the set 1, E3 is the set 2. What is common between those? And there's nothing that's shared between those two sets, right? There's not a 1 in E3 and there's not a 2 in E2. And as a result, there is no overlap. And so we have what we're going to refer to here as the empty set, right? And we can write this down as just a set that has absolutely nothing in it, right? We have our empty set over here, okay? And using that empty set is sort of indicating that there actually is no shared elements between E2 and E3. So let's talk a little bit more about the empty set then. If we have a set that contains no elements, we call that the empty set. We'll also refer to this sometimes as the null set, or in the context of probability, as the null event. So the null event, the null set, the empty set, they all refer to exactly the same thing. We're going to use this notation that looks a little bit like a 0 here, right? If you take a 0 and you cross through sort of beyond the edges of the 0, that means the empty set. And so you're free to write this in any way that you see fit, but more often than not, you're going to see the empty set written as this 0 symbol here. And the most common way that the null event is going to arise is going to be when you take the intersection between two sets that do not actually overlap. So if you have events that don't share anything in common, then their intersection is going to be the empty set. So if E1 and E2 have no shared elements, then E1 intersect E2 is the empty set. And when this happens, we refer to these events as being mutually exclusive, right? And the way we can think about this is if E1 happens, then E2 did not happen. And if E2 happens, then E1 did not happen. They can't both happen at the same time. So as a very common example, if you think about, say, rolling a die, right, then one event might be that you get an even number, one event might be that you get an odd number. There's no overlap between those two events. If you get an even number, you did not get an odd number. If you got an odd number, you did not get an even number. So they're mutually exclusive. They can't both happen. And the way that we'd write this mathematically is by saying that their intersection is going to be the empty set. The null event can also be thought of as representing an impossible realization. In some sense, what we're saying is that nothing from the sample space happened in the case of our probability discussions here. And so as a result, if the null event occurs, it means that nothing happened. It's impossible. We can't actually observe that. Okay? There's no outcomes from the sample space contained in it. Now, when we're thinking about set operations, it's good to be able to mathematically go through them, but it's also important to recognize how they relate to the real world, because ultimately what we're going to want to do is we're going to want to have sample spaces and events and ultimately probabilities that represent things in the real world for us. And so being able to use the set operations to represent language that we might actually discuss is going to be a really important consideration for us. And so a couple of things to note here. If we see a union, we should be thinking the English word or, right? So it's going to be A or B, event 1 or event 2. The union expresses this idea of or, right? So E1 union E2 means either E1 happens or E2 happens. And that's because we're going to take all of the events or all of the outcomes from both possible events here. If we see an intersection, then we should think and, right? So E1 intersect E2 means both E1 and E2 happen, right? The only way that the intersection is going to happen is if some shared outcome occurs between the two different events here. And so we need both of them to happen. We need both E1 and E2. And if we see a complement, we should be thinking not. So E1 complement means not E1. If we don't want E1 to happen, then we're thinking about E1 complement. Now, what's really important for us to notice is that we can go both ways with these relationships. So we can go from seeing a union or an intersection or a complement to a sentence about it. But also, if we're expressing something as a sentence, then we should be able to go back to express this in terms of the set notation. And that's going to be a critical direction to go because oftentimes we're going to be thinking about events in terms of their words in the real world. We want to do A or B. We want both C and D to happen. We don't want F to happen, right? And so in these cases, we're going to be thinking about the use of our elementary set operations here, translating back from sentences that we actually care about. And so let's look at some examples of doing this. So in this setup, we're going to be drawing a card at random from an ordinary deck of 52 playing cards. Okay. A is going to be the event that we see a king, so that we're drawing out a king, and it can be any king. And B is going to be the event that we draw a card that has clubs on it. Okay, and so we're drawing out one of the suits here. So we want to describe A union B in words. Now remember, the union is going to be an or. So A is the event that a king is drawn, B is the event that a club is drawn, and so A union B is going to be the event that either a king is drawn or a club is drawn. And so here we have either a king or a club. Now importantly, if it's a king and a club, this is still going to count, right? So the king of clubs is included here, right? But we have either a king or a club being drawn. What about A intersect B? Now again, intersections should always make us think and, okay? And so then with our and here, we're going to want to say A and B, a king is drawn and a club is drawn. And so the only way that we're going to have both a king and a club being drawn is if the king of clubs is drawn. And so A and B, king and club, king of clubs. How would we express the event that a king is not drawn, right? And so if we're going through this sentence here, the operative word is going to be our not here, right? We know the event that a king is drawn, right? So king is the event A, but we want not that, and so then we're thinking about that as being a complement, right? So complements correspond to nots. A complement is the event that a king is not drawn, not a king. Okay. We continue the events here. How could we express the event that either a king is drawn or a card that is not a club is drawn? Okay, so we have an or here, right? The or is sort of the first thing that jumps out to me. The or is going to be a union, so we know we need a union. And what do we need to take the union of? Well, it's either a king, so that's A, or a club that is not a club, or a card that is not a club. And so not a club is going to be B complement, right? Because B is club, not is the complement. And so what we need to do here is we need to say, well, this is A, this is B complement, and we need to union them both. So we're going to take A union B complement. How do we express the event that a king of clubs is not drawn? Well, the king of clubs, we've already actually seen, that's going to be A intersect B. But if we want to draw not the king of clubs, then we need to take the complement there, right? So A intersect B complement. When we're thinking about using intersections or unions for more than two events, we actually have a shorthand way of writing this down, right? Because sometimes we're going to have many events that we want to take unions of. We want to take everything from all of these events, or we want to find the intersection of many events. We want to see what is shared between all of these different events. And so if we have a bunch of events here, E1 up to En, then if we wanted to take the union of E1, E2 all the way up to En, then we can write this down as one big union symbol here. And so we take the huge union over here, and then we're going to be taking from 1 up to N of the different events here. And really what we should be doing here, there's a small typo on this slide, right? This should be an I here, not a J. So we're going to go from I equals 1 to N of the event EI. Okay, and so what we're saying is this is going to be the union of E1, E2, E3, all the way up to En. Okay. And if you actually wanted to take this union, the way that we can sort of functionally do it is we can take the union of E1 and E2, and then we take this set and union it with E3, and then we take that set and union it with E4 and all the way down, right? So we're taking what's shared between all of them. For intersections, we're going to do a very similar thing, except instead of writing it as one big union, we're going to write it as one big intersection. And again, the I should match the I that is in here. Okay, and so again, if you wanted to actually compute this, you take E1 intersect E2, and then you take this set and intersect it with E3, and so on and so forth, throughout all of the different sets that we have. So statistical experiments ultimately are going to be formalized through the use of sets. Right? This is through our sample space and through our events. And the elementary set operations are going to allow us to manipulate these events and combine them and contrast them in different ways, but they're also going to allow us to convert from language about the events into mathematical expressions of these. And really what that's going to enable us to do is express very complex ideas through the use of these sort of more basic building blocks, which is really going to help once we start wanting to compute probabilities about these different events.